Okay, I will have your test back on Tuesday. I was waiting for one more test, which I got like 10 minutes ago. So it's I'll have them graded this week, and I'll have them on Tuesday for you. So that won't be a problem. We actually, including tonight, we have 4 lessons left. So yeah, it's today, and then we have next week. Remember, I'm not here Thursday, so we have we'll do 12-1 and 12-2 next week, and then the week after we'll do 12-3 and 12-4, and then it's review, test, review, final. So we're almost done, actually.
Is the primary going to be open note? Okay.
It'll be you get one sheet of notes. So basically, you can take your index cards and everything else and make a sheet of notes.
Like a single sheet?
Yep.
Okay.
One full side. Yeah, it's the same concept with like the note cards. I hate open notes because you end up taking forever to try to find stuff, and you end up not studying as well because you're like, oh, I have all my notes, I'm fine. By actually having you create the worksheet, it kind of forces you to study, to write down the stuff that you're going to need. So it actually helps you more than just having open notes, believe it or not. So, all right. So tonight we're going to look at polar functions. Has anybody seen polar functions before? Okay. If you've never seen polar functions before, polar functions look like this. These are the ones on the circular graphs. So this actually is one of the more important shapes that we're going to look at. We're going to actually look at this one tonight. This one's known as a cardioid because it looks like a heart, apparently. Yeah, it is, but that's what they call it, a cardioid, because of that. We got that one, and then the other one that you'll see quite often is the, basically the flower. So actually, if I do this, you can start to see how it actually, you can increase, actually change this so it only does, nope, steps by 1. 0 to 10. So you can actually see how it actually increases the petal count as the number gets higher. So we're going to look at those two actually, because those are the two that come up quite often in our different calculations and stuff tonight. But if you've never really seen polar before, we're going to talk about a little bit about how polar works, because parametric, at least it was still on the XY plane. So it's like, yes, it was an extra term, but you're really just calculating X and Y and plotting those points. Polar is not an XY graph anymore. Polar actually uses R and theta. So your points, horrible theta. That's better. So we have our radius and our angle. So every point is based on that. So your angle is always going to be from what's known as the polar axis, which would basically be your x-axis on the coordinate plane, to the line that you're dealing with. So your angle goes up. We're not actually drawing a line, but it's going up to that point. And then the radius tells you how far out you're going to go for that one. All right. So let's actually hide that for a second. We do 3 comma I over 2. Hold on. That's fine. All right. So everyone looks like that. I want to be able to put a polar plane. Business. All right, so let's look at a couple examples of this. So the first one is 1 in 5 pi over 4. So you can start to see how my angle is going to go around 5 pi over 4. So we're past the horizontal line. We're going down to the third quadrant, basically. And I'm going out 1. So my point is right there. That's the only thing I would actually graph. I wouldn't graph the line. The line's just there to show you where it's going. The point is all you would actually graph in that situation. The next one is 2 and 3 pi. How much is in a circle? 2 pi. So 3 pi is actually going around it again. So that's going over to there, and then that would be going up 2 spaces. So that's 2 and 3 pi. That's actually the exact same as 2 and pi. So 2 and 3 pi and 2 and pi are the exact same point. Right? So you're basically, once you go around the circle, it's just repeating the point. So you can do exactly like we used to do with changing radians to degrees. It's the same concept. Every time it's 2 pi, you can just subtract those off. So 2, 3 pi and 2 pi are the exact same point. Also notice 2 is this way. Normally, if we're going that way on the x-axis, it's what? Negative. If we're going this way, that's the origin, right? If we were going this way, it'd be negative. Because the way polar works is it's telling you where you're going around the circle, it is always going in the outwards from the origin. So once we get to here, we're going out 2 spaces from there. So that is a positive 2. We're going to skip 3 for a second. I'm going to go to D just because it's going to explain what I just said here. So if I went 3 pi over 4, if it was positive 3, I'd go this way. Because it's from the origin along that line that I just got to. Since I did negative 3, I'm going the opposite direction. Okay. So this is 3 pi over 4 would be to give me that line. Positive 3 would be that way. Negative 3 is on that same linear line, just the opposite direction. So I'm going down to here. Does that make sense? All right. If we're going to a negative theta or a negative angle, we just go backwards. We're going clockwise around the circle instead of counterclockwise. So same concept here. Like if you went 3 pi over 4 here, I can do pi over 4 here and get the same point. If I did negative pi over 4 and 3, that would be the same point there. So there's multiple points that are going to be the exact same place. So if we go back and we look at my rows that I did, or my flower that I did here, if we did 0 to pi, that's all it is. If we did 0 to 2 pi, I've got my whole thing. If I did 0 to 4 pi, it doesn't change. Even if I did 0 to 3 pi, it doesn't change because it's just re-going over a spot that I've already done. Okay? Any questions with that? Does that make sense? Okay. We can convert our points back and forth. So there is equations for them, and these are going to come up when we start to look at the actual trig function, or not the trig functions, the calculus equations for arc length and area. These come up in it because we're changing basically from our Cartesian mindset to a polar mindset. So we have 2 sets of equations. If we're going from a Cartesian point, or actually backwards, if we're going from a polar to our Cartesian, this is this one here. So this is polar to, actually, I'm just going to put XY. It's easier than writing Cartesian. So if I got a polar and I want to go to the XY coordinates, I would use this. X is r cosine theta, and Y is r sine theta. If I have XY and I want to go to polar, I'm going to use these down here. So this is XY to polar. So your radius is just the Pythagorean theorem. It's x squared plus y squared. And your theta is actually going to be the arctangent of y over x because I need to find theta. We're going to do a problem for each of these in a second. So sometimes it's easier to have it done in polar to figure it out. Sometimes it's easier to be done in the XY coordinate. But having the option of going back and forth is kind of nice. And while these are going to allow me to do points, they also can do functions as well. So we can replace x in a function with our cosine theta and y with our sine theta and solve, and actually get an equation replaced into a polar equation. You just solve it for r at the end. All right, so let's look at a couple, just switching them back and forth so you can see how that works. So I've got 2 and then pi over 3. And I want my xy coordinate. So we remember, so it said x was r cosine theta and y was r sine theta. So x is 2 times cosine of pi over 3. And y is 2 times sine of pi over 3. So what is cosine of pi over 3? Yeah, square root of 3 over 2. So to easily remember this, sine starts at 0 and goes to 1. So it's increasing in value as it goes. So pi over 6 is square root of 3 over 3, square root of 2 over 3, or square root of 2 over 2, and then square root of 3 over 2. Or, no, sorry, rephrase this. 1/2. It was 1/2, not square root of 3 over 3. That's tangent. 1/2 square root of 2 over 2, and then square root of 3 over 2. Cosine does the reverse of that. So it starts at 1/2 and then goes down. So this one is square root of 3 over 2. I think I got it backwards. I got it backwards. Hold on. Let me look at the unit circle just to make sure. Square root of 2 is in the middle. That one's in the middle. That's the easy one.
So is it 1/2?
Yeah, I think it's 1/2.
I'm looking at it right now.
Yeah.
Question.
Yeah, 1/2. Yes,
For the exams, would we be able to think out the unit circle as like a separate?
I'll give it to you.
Okay.
Remember. Yeah, if you're gonna like for these, I'll give it to you because you're gonna need it on some of this stuff. So I know it's it. The trick for it, actually, if you ever want to, actually, I don't even know the hand trick. So, well, you could do that too.
I used to memorize it. Then I just
Look it up. So if you think about it, so this would be the y's. So this is yeah, it's 2 over 4. It's with 4s. Oh, I didn't switch back. All right, I'm just gonna leave that there. You can do it if you get them all to 4s. It's like it just goes basically down the list. It's like 1, 2, 3, 4. Yeah, it's the square root of 1, square root of 2, square root of 3, square root of 4 over 2, and then backwards. All right, so cosine, this is 1/2. And sine, this is square root of 3 over 2. So my x will be 1, and my y would be square root of 3. So this point is 1 and square root of 3. So we can change from polar to Cartesian and get the same point. So if we look at it, you're going to have that same exact point in on the spot in the graph. And actually, in Desmos, that's actually how you have to graph it, because it won't let you graph a polar coordinate. You actually have to change it to the xy. But you can do it with that formula. You can put the r cosine, and it'll actually change it over in the right spot. All right, let's look at the other direction. So in this case, I've got my xy, and I'm going to my polar. So r squared equals x squared plus y squared. And tangent of theta equals y over x. So my r, so I have r squared equals 1 squared plus negative 1 squared. So I get 2. So r is going to be the square root of 2. When we're doing our tangent, we have tangent of theta equals negative 1 over 1. So we're actually looking at the arctangent, in this case, of negative 1. So to get arctangent of negative 1, when my y, so this one right here is in the 4th quadrant. That matters because the arctangent of the value will give you the 2nd quadrant or the 4th quadrant in this situation. So since this is in the 4th quadrant, it's going to be 7 pi over 4. And I just closed my tab. Okay. So this is 7 pi over 4. Or you also could have done negative pi over 4, depending which direction you wanted to go. So to graph a point in Desmos, you have to have it in the xy coordinate. To graph the functions in Desmos, you just type it in as r equals, and it'll graph it. So, but your points, you actually have to do. So when we had the last one, it was 2 cosine. So you actually have to graph this as 2 cosine pi over 3, comma 2 sine pi over 3. You have to graph it like that. Graph the point in Desmos. So you have to basically almost convert it to xy coordinates to actually graph it in Desmos in the right spot. And that point was the same as 1 square root of 3. So if we were to graph 1 comma square root of 3, it's in the same spot. All right. All right. Now let's look at a couple equations. What do you think this would look like if I just said r equals 2? So in a Cartesian plane, if I just said y equals 5, what do I have? What kind of line? It's a horizontal line, right? Because the x doesn't matter with this. It's always y equals 5. And if I said x equals 2, it'd be a vertical line. The y doesn't matter, right? So what is r equal 2 going to give you on a polar graph?
Oh no, it's circle.
It's going to be a circle. Because what doesn't matter? The radius is always 2. Theta doesn't matter.
It didn't specify, I guess, what the origin was. So
It's always at the origin. So the polar will always be at starting at the origin. So r equals 2 is just a circle with radius 2. So in polar, to draw a circle, you just tell me the radius. So if I want a radius of 1/2, it's 1/2. A radius of 5, 5. Because my circle, it's the theta doesn't change. The theta is all, just like y equals 5, it's all the x's. It doesn't matter what x is, that's there. In this case, that's what you're going to get with r equals 5. Or whatever this one was, r equals 2. Now, I can't graph this on Desmos, but if you do theta equals a number, so let's say theta equals pi over 4. What do you think that's going to give you?
Radial one.
Yeah, it's going to be a line. It's literally going to be a straight line at pi over 4, but going forever. Because again, in this case, radius doesn't matter. There's no radius variable in it, so radius will go on forever. So it's basically a line going through that on that angle.
Would it also be like behind?
Yep, it'll do the negative side as well. Because remember, radius could be negative. So actually, that I can show you on here. So we have r equals 2, right? If I do r equals -2, it doesn't change. Because it's just going the opposite direction, but it's still doing all the things. So you can have negative radiuses, it's just going in the opposite direction, but it's still, because we're going in a circle, it's in essence the exact same thing. Okay. All right. We kind of already looked at this one, but we're going to look at it a little bit more. This is the cardioid. So we're going to look back at this. So the cardioid is 1 plus sine theta. Because if I just did sine theta, I'd have a circle. All right, so let's look at this just from 0 to pi over 2. Oh no, the less than or equal to in this case is just to get the shading.
Oh.
If I make this equal, the only difference is it doesn't give me the shading.
Oh.
So the shading kind of makes it a little easier to see things. So I left the shading out for this one. Although when I'm doing the cosine one, it won't work with the actual less than or equal to, and I don't know why. It gives me something different, and I haven't quite figured out why that's the case. So I got rid of the less than or equal to in that one. So what this says is basically Let's go around this and let's see what's happening. So at 0 degrees theta or 0 radians, what's sine? Sine is 0, right? So 1 plus 0 is 1. And that gives me that's that point right there. Okay? So that's this point, like right here. That's that point right there. Okay? So now, as my radius or as my angle gets bigger, so at pi over 6 for sine, that was 1/2, right? So we're right there. So now that's 1.5. And that kind of makes sense. That radius is still 1.5. It's increasing. When we get up to pi over 3, that's square root of 3 over 2. It's bigger. And when we get to pi over 2, we're at 1. We're at positive 1. So 1 plus 1 is 2. Okay? As we go past that, what happens? So as we go past pi over 2, what's happening this side? Not yet.
Yeah, it decreases.
It starts decreasing. So my derivative is negative, yes. But the function is not. So if we go to pi, we now have the other side of this one, right? It's basically the exact same, it's symmetric. It's just coming down. Okay. All right, so now now we've done the first 2 quadrants. As I move into the third quadrant, now my signs are what? Now my signs are negative. So I'm now going to be subtracting from 1. Okay? So if I go to 3 pi over 2. So you can see this one's a lot smaller now because they were basically subtracting from 1. And when I get to 3 pi over 2, I'm at negative 1, correct? 1 minus 1 is 0. And that's where I'm right there. Okay? And now if I could finish out and go to my 2 pi, I'm going back up. So my negative, it's still the negative values, but my negative values are getting smaller. So I'm going back out to that 0 point. Okay. All right. Any questions on that? Does that make sense on how it works?
Like the sine graph is only a circle above because the negative values just go to the other side. For like R equals.
Oh, if it was just R equals sine? Yeah, hold on a second. I'll show you.
It just like loops back on the same circle.
Yeah, so if I had that. See how you have sine of 0 to pi is still a circle? Pi over 2 gives me half a circle. Pi gives me the full circle. So when I did the negative values, it's the angle is the exact same thing. It's just going backwards around it. So that's why it doesn't change.
So if you do like pi to pi over half, it'll be just the left side of the circle.
So you'd actually have to do pi over 2. You get, yeah.
No, like the range is pi to 3 pi over 2.
It's not a full circle because you already have the circle.
Sorry, pi.
Oh, pi. Yes, yes. Why is it?
The point that's
I don't know why it didn't actually graph it.
like that.
It didn't like that.
Oh, pi.
Hold on. There we go.
Oh, it's still on there.
It does stuff when it's less than or equal to it. It's like it's really weird. So yeah, it's that side. And then if I did it to 2 pi, it's this full circle. So it's literally just looping it around it. So, okay. All right. this one, so the next one we're going to look at is what I basically already looked at a little bit ago. This is my flower. So this one does go from 0 to 2 pi. So pi is it does change from 0 to 2 pi. The circle for this one, or the A, so the number in front of the theta has an impact on it. So if it was 1, it's just a circle. Okay, it's a circle rotated back 90 degrees because that's exactly what cosine is to sine. Okay, cosine is shifted 90 degrees. And that's what you see here. As I increase to 2, I have 4 leaves. If I go to 3, I only have 3 leaves. And we notice if I do 0 to pi, it's the same as if I do 0 to 2 pi. So when you do cosine of 3 theta, it actually loops over itself again. So there's 6 leaves there. They're just on top of each other. Okay. Why does that matter? And why am I spending a ton of time talking about this? Is because when we start to look for area, which is the next thing we're going to move into, knowing the interval that you're looking at is going to be very important. Okay. So for this one, if I just wanted this little piece over here, so I just want that one leaf right there. Notice it's symmetric on the top and the bottom. So really, I only need to find that part up there. So I need to find the interval that's going to give me that piece. So when I find the area, I'm just looking for that. Where when we're looking at the third one, since it doubles it, we have to keep that in mind for it. So those are just the little things that you have to keep in mind, and how you figure things out is what's happening. And Desmos makes it nice to play with it because we can sit there and go, okay, we've got this. 0 to pi is going to give me the exact same thing. I really just want one of the leaves. So let's say if I do 0 to pi over 3, that's still giving me too much of a stuff. So 0 to pi over 6, that gives me what I want. So that would be the interval that I'd look at. I'd find the 0 to pi over 6. And then if I was looking at the entire shape, I would just multiply that answer that I got by 6. And I have the area of the entire flower. Okay. So using Desmos to play with the intervals to find the piece of what you want is going to be helpful. Huh? No, it'll actually happen at any odd one. Any odd number. So any odd number doubles over on itself. So it's only 0 to pi. Any even one, you have them all. So yeah, so there's 5, 6, 7, 8, 9, 10. So in essence, like I said, they're all doubled. So 10, there's 20 leaves there. 9, there's 18 leaves there. They're just on top of each other. Okay. So yeah, it's the even ones, you're going to see them all. The odd ones are 0 to pi. So for this one, if I wanted to figure out the area of this entire shape, I just want to find that part up there. So pi is going to be half. Pi over 2 is that piece. So let's do pi over 4. So 0 to pi over 4 is going to give me that part right there. So and if I wanted to find the whole thing, that was that piece, I'd multiply it by 8 to get the area of the entire shape. Okay. Good, because that's literally the next question. We're going to look at area. All right. Area of polar shapes. So the formula for area is very similar to what we had done before. It's going to be 1/2 r squared d theta. So r is your function in terms of theta. So my interval that I'm going to have are in terms of theta. So in this case, this one's looking at from A to B. So theta is A to theta is B. Think of that as just like your x's. What was your beginning? What was your end? Same thing when we're rotating. What's your beginning? What's your end? So all we're doing is basically squaring what your radius is and figuring out the integral of it. It's not all real numbers. I don't know what that one is. It's a fancy R. Let's see if I can find, let's see if it tells me what it is. Because I actually don't know the name of that one. Oh, they just used it to, it's the bounded region. They just made it a fancy looking R. So one of the things, so this is actually, people are talking about like how you write books and stuff like that. And what do you do for people who can't like necessarily see the pictures and stuff? So all books are now required to have a description of the picture. So for screen readers, it can read this and describe what the picture is, so people can see it if they can't, or people can understand what's going on if they can't see. So they all have to do that now, which is good. I think that's a good thing. All right, so that's our formula for area. So let's find the area of one leaf. All right, so we've got our R is cosine of 2 theta. And we just figured out what the area or the range that I'm going to use is, right? Or the interval was for this one. We were doing 0 to pi over 4. Because that was going to give me the top half of that leaf, right? So 0 to pi over 4 is going to give me the top half of that leaf. So if I'm looking for one loop, they only want one of the loops. We're going to take whatever this answer is and just multiply it by 2. Because that will give me one full loop of that flower. Okay. So I've got my integral from 0 to pi over 4. I'm going to multiply it by 2. And it is cosine of 2 theta squared d theta.
Oh, never mind.
Well, because yeah, the question's asking for only one of the leaves. If we were looking for the entire flower, then I'd multiply it by 8 to find the whole flower. But they only want one of the loops of this one. All right. So how do I do my integral of this? So this, actually, I'm going to rewrite this slightly. This is the same thing as saying 2 or cosine squared of 2 theta. So it's those are the same thing. So you're not squaring the 2 theta. You're squaring the cosine. So remember, I can't find the integral of cosine squared, right? We have to do what? We have to use one of those special theta integral rules, or not integral rules, of trig rules, the trig identities. So I need to get rid of that square. So cosine squared theta equals what that doesn't have a squared in it? There should be if you have the book, at the very back of the book, there should be a table of all these values, all these formulas. It is the half angle formula. So 1/2 and 1 plus. I always get that mixed up. 1 plus. Cosine of 2 theta. So I already have 2 theta here. So this is actually the integral of 1/2 1 plus cosine of 4 theta. 2 theta. Oh, I forgot that 1/2 when I wrote my equation. So I pull out the 1/2 and that 2 is gone. There we go. I'm like, I knew the answer. Yeah. Yes.
That instead of it?
You actually are using that in this because that's how you get the 4 theta. You can't use the cosine u to get rid of the squared thing.
As the equation of cosine square u is equal to 1/2 u plus 1/4 sine 2u.
Cosine squared. They actually gave you a formula for cosine squared.
Yeah.
I let's see what it comes out to be. I guess you could use it if you want to try to remember it. So it probably does come out to be the same. If you notice in the book, there's probably like 180 something integral rules. Yeah, there's a ton of them. So yes, there are rules for them all. Most of the rules, though, and actually, I'll show you real quick. That's not what I wanted. So most of the rules that they give you, some of them you actually have to use, like the ones that there's some of them that we've actually talked about specifically. Let's see if this actually comes up. Well, while that's coming up, we'll finish this and then I'll go back to it. We can pull out the 1/2 here. So I have 1 plus cosine for theta. So that equals 1/2 theta plus 1/4 sine 4 theta. And we're going 0 to pi over 4. Yeah. Wanted to make sure I got my signs right. Maybe they don't give it to there. Now, what was the equation they gave you?
Just cosine square of mu du is equal to 1/2 of u plus 1.
Yep, that's right. Because my u was 2 theta. So that's why that comes in. So it was the same. Yeah, here. Let's go back. Yeah, here's it can show us. So here's the trig rules. So here's all the trig ones. Here's the inverse trig ones. There's the exponential logarithm ones. So now up to 120 different integrals they give you in the back of the book. So, and that's the thing. It's like you can sit there and try to remember them all or find like, okay, this is the perfect one to use. The problem is that you're never going to remember them all. So being able to take things and manipulate it using stuff that's a little more easy to remember with like the trig rules and stuff like that is helpful. In the end, if that's what you ended up using on the thing, if you wrote that in your test, use that, that's fine. It's not big, that's big of a deal. Either way would work. You still come up with the same answer at the end. All right, so we've got that. Now I got to plug in my 0 and my pi over 4. Okay, back to here. So if I plug in pi over 4, I get 1/2 pi over 4. Which sign of pi is 0, right? Sign of pi is 0. So because it's pi over 4 times 4, which is pi, so sine of pi is 0, so that's 0. If I plug in 0, that's 0. Sine of 0 is 0. So the answer is pi over 8. So one loop area is pi over 8. And what was the other one? I'm just setting up the next problem on the Cosmos. The 3 sine theta. All right. When you're using Desmos, you have to make sure you put what it is. So like you can't just put 3 sine theta. If you put y equals 3 sine theta, then it gives you that. You have to tell it that it's an r. So this way it knows which function you're doing. So here is my, actually, let me change the color of the second one so you can see it a little better. So the next problem that we're looking at wants me to find the area in between the two shapes, or not in between. So that's up here. So we're looking for the area in here. So what do I need to do to find that? So we're subtracting them, right? And we're looking for the thing. We're going to subtract those. But before we do that, what do I need to figure out? What was the first thing I had to do in my last problem? I knew what the integral was going to be, but what did I need to find to actually do the integration? I needed to find the interval. I needed to find the a and the b. So in this one, I got to do the same thing. So I need to figure out where these two intersect. So they intersect twice, but I need to figure out where they intersect. Desmos doesn't allow you to do that. Okay, so you can't, unlike the coordinate plane where you can just click and go, oh, it's right there. It doesn't work when you're doing polar. So we've got to find the intersection points. How do I find when two things intersect? That means they are what? They're equal to each other. So I have 3 sine theta equals 1 plus sine theta. So I have 2 sine theta equals 1. So sine theta equals 1/2. So which values of theta will give me sine of 1/2? Which values of theta will give me sine as 1/2? 5 or 6? Back. Fine. So pi over 6 and 5 pi over 6. So those are my two intersection points. So my integral is 1/2. Now, which one was on top? The 3 sine theta was on top. So 1/2 of 3 sine theta squared minus the integral, and that's from pi over 6 to 5 pi over 6. Pi over 6 to 5 pi over 6. 1/2 1 plus sine theta squared. So we have that integral that we now have to solve. All right, so what do we do? What do you want to do? We have to square it. So, well, let's get rid of the squares. Let's do that and see what we got, right? All right, so I've got, so we'll pull out the 1/2. we'll put all this together. So I got pi over 6, 5 pi over 6 there. I've got 9 sine squared theta minus. Then we got 1 plus 2 sine theta plus sine squared theta d theta. Go. Sorry. All those are minuses. So I can put the 2 sine theta, these two together, and have negative 8 sine squared theta. Or not negative 8, positive 8. So somehow, again, just like I did with the cosine, I got to change that sign to something that I can use, right? So sine squared theta is 1/2 1 minus cosine 2 theta. So my 8 sine squared theta becomes 8 times 1/2 times 1 minus cosine 2 theta. No, sine becomes minus cosine 2 theta. It's not cosine squared, it's cosine 2 theta. That's the only difference between, so cosine squared and sine squared both become basically the exact same thing. The only difference is the sign. Cosine's positive, sine's negative. So we've got 4 times 4 minus 4 cosine 2 theta. So we now have 1/2 pi over 6 to 5 pi over 6. We have 3, because that's 4 minus 1, minus 4 cosine 2 theta, minus 2 sine theta d theta. All right, so we've got our, let's do our integral. We have 1/2 in front of us. All right, so what's the integral? What's the integral of 3? 3 theta. Cosine 2 theta. So it's going to be minus 2 sine 2 theta. Because the 1/2 comes out, 4 divided by 2 is 2. And this one becomes plus 2 cosine theta. I don't think so. Gotcha.
Subtracting one.
Oh, okay, yeah. That's how the 3 p.m. It's a 4 minus 1. All right, let's plug in our numbers. So I've got 5 pi over 2. 5 pi over 6 for, sorry, 5 pi over 3 for sine is negative square root of 3 over 2. Cosine of 5 pi over 6 is negative square root of 3 over 2. Now minus pi over 2 plus 2 sine of pi over 3 is square root of 3 over 2. Plus 2 square root of 3 over 2. Oh, sorry. Minus. What?
Why did the four shrink into a 2?
Right, the 4 turned in. Oh. Oh, because this was 1/2. So remember, you have to do your substitution? No. So that 2 theta right there, you have to do your substitution for it, and it pulls out as a 1/2.
Oh,
So 4 times 1/2. All right. I think I got all those done right. Let's see. Here comes the the big reveal at the end. So I've got 5 pi over 2 minus pi over 2, which is 4 pi over 2, which is just 2 pi. So this right here becomes square root of 3. That becomes minus square root of 3. That becomes square root of 3, and that becomes minus square root of 3, which should cancel everything out. So the answer is pi. You're like, all that work for pi, and it's not even a chocolate cream one. Now, here's one thing that we didn't do in this problem that we could have done because nobody mentioned it. And I didn't say anything on purpose. Whenever you're looking at figures like this, always look for what? Starts with an S. Symmetry.
Done it from
Pi over 6 to pi over 2.
0.
Well, I could have done basically if I did it from pi over 6 to pi over 2, which is right in the middle. What's sine of pi over 2? 0. Like it basically it's going to give me those zeros, so it's going to cancel. Well, actually, pi over 2, sine of pi over 2 is 1, but the cosine 1 0. So it's going to cancel out a bunch of stuff and make my calculations a lot easier. All right. So you can always look for symmetry, especially in polar, because it has a tendency to repeat itself all the time. All right. So you want to look for those things. All right. Two more things to go. Arc length. All right. Your formula for arc length. We have our integral from a to b, same thing as before. The square root of r squared plus the derivative of the function. So dr over d theta. So if we're looking at our cardioid, where does it start and where does it end? So what's my A and my B for this one? Yeah, it goes 0 to 2 pi. It goes all the way around. Okay, so square root. My R is 1 plus sine theta squared. And what's my derivative of this? So that's going to be the 1's gone and sine becomes cosine squared theta. Or not cosine squared, because cosine squared theta down here. So there's my integral. All right, let's do them out. Let's see what we get. So I've got 1 plus 2 sine theta plus sine squared theta plus cosine squared theta. That's just 1. So I have my integral from 0 to 2 pi of the square root of 2 plus 2 sine theta d theta. And since you can't do it, you have to use Desmos for it, and it equals 8. So the arc length of the cardioid. So as we're going, if we go all the way around the cardioid, its arc length is 8. All right, that's the only other thing we haven't found yet. Nope, we're not doing rotation. So no surface area for this. We haven't done tangents. Last one. We're almost done. All right. So the derivative of a polar function is a little more complex. It's drd theta times sine of theta plus r cosine theta over drd theta cosine theta minus r sine theta. So it actually ends up being a chain. To prove this, it ends up being using the chain rule and the actual variables of what converting it back to a Cartesian plane is in essence what they're doing. You're not going to have to do that. That's the formula for it. So when you're doing this, the first thing you're basically doing is the derivative of r. After that, it breaks down pretty simply. Because we're using that on the top and the bottom. The only thing that changes is the other stuff here. So everybody got this written down? I'm going to erase it because it's actually right there still. All right. So in this cardioid, my r is 1 plus sine theta. And the derivative of that is what? Cosine theta. So the derivative is 1 plus sine theta plus, oh, sorry, not, here first. Cosine theta, sine theta, plus 1 plus sine theta, cosine theta, over cosine theta, cosine theta, minus 1 plus sine theta, sine theta. All right. Now all we have to do this is just simplify it down. So I have cosine theta, sine theta, plus cosine theta, plus cosine theta, sine theta on the top, which simplifies down to, I have two of those. So I have cosine theta plus 2 cosine theta, sine theta, which is, if I pull up the cosine theta, 1 plus 2 sine theta. So that's the top. And if I were you, I would do it similar to this. I would literally try to simplify it down one at a time. Do the top, do the bottom, and then put them back together. So my bottom, I have cosine squared theta minus sine theta minus sine squared theta. And I've got a whole bunch of signs here, or a bunch of signs with this cosine. So if I change my cosine, I'm going to change that to 1 minus sine squared theta. So I have 1 minus sine squared theta minus sine theta minus sine squared theta, which comes into be 1 minus sine squared theta, or sine theta minus 2 sine squared theta. And that's my bottom. Oh, if you really wanted to be crazy, you can actually factor this. But I'm not going to, because you don't really need to. So that's the bottom. So my derivative of this, so we're going to take this. Equals cosine theta 1 plus, yeah, plus 2 sine theta over 1 minus sine theta minus 2 sine squared theta. So that is my dy dx. That's the derivative. Once we have the derivative, you can find any tangent you want by just plugging the values into it. I'm going to be nice. We're not going to do it. What if I wanted to find a horizontal tangent? How would I do it? Nope. It's basically what is 0? When the derivative is 0. So that means when my numerator is 0, it's going to give me a horizontal tangent. So to find my horizontal tangents, I set my numerator equal to 0. To find my vertical tangents, I do what? Right, so the denominator equal to 0. If they are both 0, it is undefined. It doesn't work. And actually, in this problem, if we did it, you're going to have 3 horizontal tangents in this problem. The one right at the top, and then you have 2 right here. So there's 3 horizontal tangents in this problem. There's 2 vertical tangents. Here and here. That point right there is actually going to be a 0 on both the horizontal tangent and the vertical tangent, and it doesn't exist. Okay. Kind of my drastic research and everything else. That's called a cusp, which I didn't realize until recently. And I always knew it was non-differentiable, but there's actually a name for it. It's called a cusp. CUSP, it's cusp. That point where it goes to a specific point.
You can have 2 horizontal.
Great.
Isn't these 2 like the lower 2?
They're going to be the exact same value, but they're at 2 different points. So yes, the horizontal, it's going to be, they're both 0 and it's going to be the same line, but since it's at 2 different points, there's 2 separate horizontal tangents. And then we have the one at the top. Right. It's it's not Haskell, but it's it's okay. So since it hits the graph twice, you're gonna have 2 of them at the 2 different points. Okay. All right. We are done with polar.
You said next class was going to be what?